So now we are going to link, right, whatever is computed by Kildall's algorithm with this particular least fixed point of f bar. Right? So we will show that in fact this mu hat k, right, that is computed by abstract forward propagate is actually the same as LFP of f bar. Okay. So so this is the abstract forward propagate algorithm, right, or the Kildall's algorithm. So our goal is to show that this mu hat k, right, this mu hat k is a map, right, it is a map from locations to abstract values, right, and we can view this mu hat k as a vector as well, right. So in that sense this mu hat k, right, this belongs to the vectorized lattice, right, which where each element of this lattice is a vector, right, whose the number of elements in the vector is the number of program locations, right. So for every program location there is one element which corresponds to the abstract value of that element, right. So it's nothing but this mu hat k. So mu hat k itself is a vector in the vectorized lattice, and what we want to show is that this mu hat k, this is the same as this LFP of f bar, right. So in a sense we have to show that mu hat k is a fixed point, right, of the function f bar, and not only that but it's also the least fixed point, right, which means that every other fixed point is greater than mu hat k. So the way we will show it is as usual, right, when you want to prove two values are equal, you prove left hand side less than or equal to right hand side, and vice versa, right. So first we will show that this mu hat k is actually less than or equal to LFP of f bar, and then later we will show the other way around, right. Okay. So the way we will prove it is we will show that this mu hat k less than or equal to LFP of f bar, this is actually a loop invariant of the outer while loop in the algorithm, right. So in the algorithm, right, there are two loops, right, one is this outer while loop and the other is this for each loop. So what we will show is that for the outer while loop this mu hat k less than or equal to LFP of f bar is a loop invariant, right, meaning that it holds when so it holds at the beginning of every iteration of this loop, right, that is what a loop invariant means, right. So including the starting iteration, okay. So you can see, right, that this mu hat k, right, this is assigned here, right, and there is a change here, right, in mu hat k. So these are the only three places where this mu hat k is assigned a value, right, it changes its value, okay. So essentially we have to show that whenever it changes its value this particular invariant always holds, right, that is less than or equal to LFP of f bar. Okay, so in order to show that something is a loop invariant you need to show multiple things, right. So you need to show that it holds at the beginning of the loop, right, which means at the beginning of the first iteration of the loop, okay. So so what happens at the beginning? So at the beginning mu hat k is initialized using these two statements, right. So at the location L0 it is initialized to alpha of p where p is the precondition, right. So this is the initial set of program states, right, or the initial valuations of the program variables with which you want to analyze the program, right. So at the location L0 I have the set of concrete program states, right, which are given by the set of states p, okay. And mu hat k is obtained by applying the abstraction function on p, right, and mu hat k for every other location L is bought, okay. So if you look at this vector, right, mu hat k at the beginning, so I have this alpha of p at location L0 and then at every other location I have bought, okay. So this is the initial value of this mu hat k vector, okay. Now this LFP of f bar, right, so we know something about this LFP of f bar. In particular we know that LFP of f bar at the location L0 is equal to D0, right, where D0 is the initial abstract value, right, that we begin the abstract interpretation with, right. And we also know, right, that this alpha of p, right, this is guaranteed to be less than or equal to D0 because that is the value, right, that you will pick. So remember that when we defined soundness of abstract interpretation, right, so we said that we are going to start the abstract interpretation, right, at the location L0 with an abstract value which over approximates the initial set of program states, right. So D0 will always be greater than or equal to alpha of p, right, and at every other location, right, LFP of f bar may have some value, but I know that bot is the minimum element, right. So it is guaranteed to be less than or equal to every other element in the lattice, right. So in other words, right, this lattice LFP of f bar, right, rather this particular element LFP of f bar this is going to have d0 at the location L0 and some values, right, but alpha of p we know is less than or equal to d0, right, this is because this is how we have picked d0, and bot is less than or equal to every other element, right, because bot is the minimum element. So at the beginning we know that this mu hat k therefore is actually less than or equal to LFP of f bar. Okay. So for every location L, mu hat k of L is less than or equal to LFP of f bar at the location L. Okay. So now the next thing we have to show is that it is a loop invariant, right, meaning that if you recall, right, the property of loop invariants. So essentially we have to show that if you execute the body of this loop, right, so if I is the loop invariant, right, so I and f, where f is the loop conditional, right, C is the body of the loop and I is the loop invariant, right. So this should be a valid whole triple, right, meaning that if you execute the body of the loop, right, in a state which satisfies I and f, right, then after you execute the body of the loop, I should still hold. Okay. So this is what we have to show. Okay. So we can assume, right, that the loop invariant holds at the beginning of some iteration of this loop, and the fact that this loop conditional also holds, right. So S is not equal to 5, meaning we are entering the body of the loop. Then you execute the body once, right, and then you have to check that at the end mu hat k should also, I mean the loop invariant I should also hold. Right. So in our case the loop invariant is mu hat k less than or equal to LFP of f bar. So we will assume that that holds at the beginning and then show that it holds at the end of the iteration. Okay. So assuming that the claim holds at the beginning of some iteration, right, let us use some notation now, right. So let me define these two notations d bar and g bar, right. So mu hat k is d bar and LFP of f bar is g bar, right. So this mu hat k is the value at the beginning of the body, right. So we know that the value of mu hat k is going to change, right. So in particular this statement is going to change the value of mu hat k for some locations, right, because this is actually inside a loop, right. So there is the inner for loop, right, which changes the value of mu hat k at some locations. Okay. So at the beginning, right, since we have assumed that the loop invariant holds, therefore we have d bar less than or equal to g bar, right. So this is in fact our loop invariant, right, mu hat k less than or equal to LFP of f bar. Okay. Okay, so now let us calculate, right. So what happens during the iteration? Okay. So during the body of the loop, right. So so during an execution of the body of the loop, so since we know that S is not equal to empty, right, because we have actually entered the loop and the loop conditional holds, right, therefore some location L will be chosen, right, and then there is this inner for loop, right. So for this location L, right, this inner for loop essentially propagates the abstract value to each of its successors, right. So whatever is the abstract value at the location L, which is mu hat k of L, right. So according to our notation, this is d bar of L, right. So remember d bar is equal to mu hat k, right, and then LFP of f bar is equal to g bar. Okay. So this value which is at location L is going to be propagated to each of its successors, right, by this for each loop, and the way that happens is that you first, right, so you basically take the value at the location L and then apply the abstract transfer function of the program command, right, which is labeling the edge, right, to the successor, and then you compute this new value f, and if this value f is not already less than or equal to mu hat k at that location L prime, then you update the value of mu hat k at the location L prime, right, by taking the join of the original value with this value f, right. And there is some modification to S, but that does not matter for us, right, because all we care about is this, we want to track the modifications to mu hat k. Okay. So we know that d bar is less than or equal to g bar, right, and we want to show that the new value, right, at mu hat k is also less than or equal to g bar. Okay. So now you can see that for some location L prime, right, we are going to change the value, right. So if this particular if statement, right, is never executed, right, meaning that the value of mu hat k is never changed, then we do not have to do anything, right, because we already know that the value of mu hat k, right, at the beginning of the iteration is actually less than or equal to g bar, and if the value does not change, then we do not have to do anything, right, because it will continue to remain less than or equal to g bar. So remember g bar is fixed, right, this is the least fixed point of the function f bar. Okay. So we only have to worry if we do enter this if block, right, and this particular statement is executed, right, which means that the value of mu hat k changes, but how does it change, right. So this new value of mu hat k at the location L prime, this is the least upper bound, right, of two values, right, the original value and the value f. Okay. So essentially what we need to show, right, is that this new value, right, which is mu hat k of at location L prime joined with f, this is less than or equal to g bar at the location L prime. Okay. So if we can show this, then we are done, right, because this is the new value of mu hat k at the location L prime, right. So remember, this mu hat k is nothing but d bar, so I can use d bar here, right. So d bar at L prime joined with f should be less than or equal to g bar of L prime. Okay. Now whenever you want to show that some value is greater than or equal to the least upper bound, right, essentially you have to show that this g bar of L prime is the upper bound of both of these things, right. So if it is the upper bound of both, then it will be greater than or equal to the least upper bound, right, of the two values, right. So essentially we have to show that this d bar at L prime, this is less than or equal to g bar at L prime, and this f is less than or equal to g bar at L prime, right. So if we can show this, right, then that means that g bar of L prime is an upper bound of d bar of L prime and f, which means it will be greater than or equal to the least upper bound of these two values. Okay. So this, right, d bar of L prime less than or equal to g bar of L prime, this is directly coming from the fact that this is what we assumed, right. So we assume that d bar is less than or equal to g bar, right. So if you call this as 1, right, so from 1 this is directly apparent, right, because d bar less than or equal to g bar means that for all locations, right, d bar at that location is less than or equal to g bar at that location, which means for that location L prime as well, d bar of L prime is less than or equal to g bar of L prime. Okay. So now the only thing we need to show is this, right, that f is less than or equal to g bar at L prime. Now let us see how f is computed. Okay. So f is some abstract transfer function, right. So if you take this location L prime, right, so you consider the abstract transfer function of this program statement C, right, and you apply f at C, right, on mu hat k of L. Okay. So mu hat k of L is nothing but d bar. So from 1, okay, so we know that d bar at L, right, is less than or equal to g bar at L, because this, that's what we have assumed, right, d bar is less than or equal to g bar. Now here I am using the fact or I am rather uh, considering the element at the location L, right. So earlier I had considered the element at the location L prime, but here I am considering the element at the location L, right, and the reason that I am doing this is because f is computed by applying f at C on d bar at the location L, right, mu hat k of L is nothing but d bar of L. So we know something else, right, so we know that f bar, rather f hat C is monotonic, right. So remember, we are in a monotonic abstract interpretation framework, right. So since f at C is monotonic, I can apply f at C on both directions, right. So I will get f at C of d bar of L, this is less than or equal to f at C of g bar of L. Okay. So f at C of d bar of L is nothing but f, right. So f is less than or equal to f at C of g bar of L. Okay. Okay. So now what is the relationship between g bar of L prime and g bar of L, right. So remember, g bar is the least fixed point of f bar, right, so which means it is also a fixed point, and if you recall, right, this f bar function, right, this function which is over the vectorized lattice, this essentially encodes those data flow equations, right, that we had defined. So we know, right, that from the definition of f bar, we know that g bar at the location L prime, this is going to be this join of f hat C of g bar at the location L for every predecessor, right, LC L prime, LC L prime, which belongs to T. Right. So for every predecessor of the location L, right, you compute this f at C of g bar of L, and then you take the least upper bound, that will be g bar of L prime. This is from the definition of the f bar function, right, and the fact that this LF g bar is the fixed point of the f bar, right. So now now you can directly see the required result, right, because see, what we need to show is that so we know that f is less than or equal to f at C of g bar at L, and I know that this g bar of L prime, this is the least upper bound, right, of this f at C of g bar of L, which means it's also an upper bound, right. So from the definition of f bar, so we get that g bar at the location L prime, this is greater than or equal to f at C of g bar G bar at L. Okay. So now if you combine these two things, right, so we have the fact that G bar of L prime is greater than or equal to f at C of G bar of L, and f at C of G bar of L is greater than or equal to f. So therefore G bar of L prime is greater than or equal to f, right, which is what we wanted to show, right, that G bar of L prime is greater than or equal to f. So this finishes the proof, right, that essentially we have shown that the new value, right, of mu hat k at the location L prime is also less than or equal to LFP of f bar, right, which means that this mu hat k less than or equal to LFP of f bar is actually loop invariant. Okay. So now let us prove the other direction, right. So now we have to show that this mu hat k, this is also greater than or equal to LFP of f bar. Okay. So that's what we will show, right, that mu hat k is greater than or equal to LFP of f bar. So for this we are going to use, so we are going to take a slightly circuitous route, because this is clearly not a loop invariant, right, because as you can see, right, at the beginning of the loop mu hat k is actually assigned bot, right, for most locations, right, except the start location it's assigned bot, and there is no guarantee, right, that bot will be greater than or equal to some value. So we cannot take this as a loop invariant, right. So what we are going to do is we are going to use the Naster-Tarski fixed point theorem, right. So what we will show is that when this algorithm terminates, right, so when this loop terminates in particular, the final value of mu hat k, right, at the end of the loop, at the end of the last iteration of the loop, this is a post fixed point of f bar. Okay. So post fixed point of f bar, meaning that f bar applied on this mu hat k is less than or equal to mu hat k. So this is the definition of a post fixed point, right. So remember, mu hat k is a vector, right, and f bar is a function from over the vectorized lattice, right. So it's from d bar to d bar. So I can apply f bar on mu hat k, right, and if I can show that the final value of mu hat k is a post fixed point of f bar, meaning that f bar of mu hat k is less than or equal to mu hat k, then I can use Naster-Tarski fixed point theorem, right. So the Naster-Tarski fixed point theorem says that this least fixed point of f bar is the greatest lower bound of all post fixed points. Okay. So least fixed point of f bar is the greatest lower bound, meaning it is a lower bound of all the post fixed points, right. So if I can show that this mu hat k is also a post fixed point, that will mean that LFP of f bar is less than or equal to mu hat k, right, because mu hat k is a post fixed point, and Naster-Tarski fixed point theorem says that LFP of f bar is the greatest lower bound of all post fixed points, right. So therefore what I really have to show is that mu hat of k at the end of the loop is actually the post fixed point of f bar. So in order to prove this, right, we are going to come up with another loop invariant, right, for the outer while loop. So this is a second loop invariant. So we have already seen one loop invariant. Now this is another loop invariant, and this loop invariant will help us to show that mu hat k is actually a post fixed point of f bar. So what is this loop invariant? So here is the loop invariant, right. So this loop invariant says that if you consider every location, right, that is present in L minus S, okay, so L is the set of all locations in the program, and S is this set, right, that is maintained by the algorithm. So we are considering locations that are not present in S, right, so which are present in L minus S, right. So for every location which is not present in S, right, essentially what we are saying is that the value, the abstract value at those locations has been propagated to its successor, right. So we know that what this algorithm does, right, is that it picks a location from S, right, and then it propagates that value to all of the successors, and then it will remove it, right, from the location L, from the set S, right. So it picks the location L from the set S, and then it removes it from S, right, and then propagates the value to all of its successors, right. So essentially all we are saying is that for every location that is not in S, right, its value must have been propagated to all of its successors, right. So this is what is captured by this particular loop invariant, right. So for all locations which are not in S, right, if you take every successor of those locations, right, so if L prime is a successor of L, then the value, right, mu hat k at the location L prime must be greater than or equal to f at C of mu hat k of L, right. So this f at C of mu hat k of L, this is what we mean by propagating the value, right, the abstract value at the location L to the location L prime through through the program statement, right, which is labeling the edge from L to L prime. Okay. So this mu hat k at L prime is considering the effect, right, uh, of all the so essentially for every successor L prime, right, this mu hat k at L prime considers the effect of mu hat k of L. Okay. So we want to show that this is a loop invariant. Now how does this actually help us, right? So how to connect this loop invariant with what we want to prove, right, which is that this mu hat k is a post fixed point of f bar. Okay. So if this is the loop invariant, right, what is going to happen when you exit the loop, right? So when you exit the loop, I know that S is empty, right? So this is the only case where you exit the loop. So if S is empty, that essentially means that I can remove this S here, right? And now all we are saying is that for every pair of locations L and L prime, right, such that there is an edge from L to L prime, this mu hat k at L prime is greater than or equal to f at C of mu hat k of L. Okay. So that's what you get, right? So on exiting the loop, we have this particular property, right, that for every edge, right, for every pair of successors, or rather for every pair of adjacent locations, right, L C L prime belongs to T, mu hat k of L prime is greater than or equal to f at C of mu hat k of L. Okay. Now how does this help us? Right, so remember again, right, so what we had shown, right, is that so we know that this f bar function, right, this is essentially encoding the data flow equations, right, that we have seen earlier. Right. So in particular, this f bar at the location L prime, right. So in particular, f bar at the location L prime, this is going to be okay. So f bar is a function, right. So if you take f bar of mu hat k, right. So if you apply f bar on mu hat k, right, and then you take the value at the location L prime, this is nothing but the join, right, of consider every predecessor, right, L of the location L prime, right, and then apply f at C to mu hat k of L. Okay. So this is the definition, right, of the function f bar, right, it just encodes the data flow equation. So f bar applied on mu hat k, right, so this itself is a new vector now, right, and this vector projected at the location L prime, the value is going to be this join, right, of taking every predecessor L of the location L prime and then applying f at C of mu hat k of L. Okay. So okay, so what have we shown, right? So by proving that this is a loop invariant, right, we will be able to show that this mu hat k of L prime is greater than or equal to f at C of mu hat k of L. Right? So what this means is that if you take, right, so let us take the location okay. So we take the location L prime, right, and let's consider every predecessor, right, to this location L, rather to the location L prime. Right? So this is the location L prime. We consider every predecessor to the location L, right. So I know that mu hat k at the location L prime, this is greater than or equal to f at C of mu hat k of L, right. So if I take the abstract value at each of these locations, right, and I apply the abstract transfer function of the corresponding program command, this mu hat k of L prime is going to be greater than or equal to the abstract transfer function applied on the mu hat k values at the predecessor locations, right. So which means that, see, this mu hat k of L prime, this is greater than or equal to each of these terms, right. So for every predecessor L of the location L prime, mu hat k at L prime is actually greater than or equal to f at C of mu hat k of L. This is what we get from the loop invariant, which means that mu hat k at L prime will also be greater than or equal to the least upper bound of these values, right. So mu hat k of L prime is an upper bound, right, of all of these values, therefore it will also be greater than or equal to the least upper bound, right. So that's the property of the least upper bound, right, which is that it is the smallest among all the upper bounds, right. So which means that this mu hat k of L prime is greater than or equal to this least upper bound of f at C of mu hat k of L, right. And now this is nothing but, right, as we just saw, right, this is nothing but f bar of mu hat k at the location L prime, right. So this means that mu hat k at the location L prime, this is actually greater than or equal to f bar applied to mu hat k and then projecting that at the location L prime, right. So and this is true for all locations L prime. So this essentially means that mu hat k is greater than or equal to f bar applied on mu hat k, right, and this means that mu hat k is a post fixed point. Okay. So so therefore proving this as a loop invariant, right, will help us to show that mu hat k is a post fixed point, which in turn helps us to show that it is greater than or equal to the least fixed point of f bar. Okay. So now the only thing that is remaining is to show that this is actually a loop invariant. Okay. So as usual, right, I mean, if you want to show that this is a loop invariant, we have to show that it holds at the beginning, right, at the start of the loop, which means at the beginning of the first iteration, and then it continues to hold at the beginning of every iteration. Right. So what happens at the beginning? Okay. So at the beginning you can see that the location, the set S, right, it only contains the location L0, okay, and for every other location the value of mu hat k is equal to bot. Okay. So which means that for every other location, right, what I need to show, right, is this, right, that so for every location that is not in S, right, I need to show that if, right, so if you propagate the abstract value from those locations to its successor, right, so for every successor L prime such that L C L prime belongs to T, mu hat k at L prime is greater than or equal to f at C of mu hat k of L, right. So for every other location except L0, right, I know that the value of mu hat k of L is bot, right. So essentially this value is bot, okay, and if you assume, right, that f at C of bot is equal to bot, and this is in general a safe assumption, right, because remember bot is the bottom element in the lattice, right. So typically the abstract transfer functions will never assign a non-bot value, right, to bot, okay. So which means that this f at C of bot, right, this will be bot, and therefore this mu hat k at L prime is guaranteed to be greater than or equal to bot, right, because bot is the minimum element, okay. So assuming, right, that f at C of bot is equal to bot, we are able to show that at the beginning, right, of the loop this particular loop invariant holds. Okay. Now you might ask, okay, what happens if f at C of bot is not equal to bot? So in this case what we can do is we can simply initialize this S with the entire set L itself, right? So that's also fine. Okay. So if you initialize this set S, right, with the entire set of locations L, right, that means that we will essentially also propagate bot, right. So here by initializing S to L0 we are only propagating the start value, right, which is alpha of P from L0 to its successors, right, and then eventually propagating to other successors and so on, right. But if f at C of bot is not equal to bot, you may also have to propagate bot, right, from other locations. Okay. So in which case if we will initialize S with L, and then this loop invariant holds trivially, right, because there is no location that is present outside S. Okay. Okay. So now we need to show that this loop invariant holds in general, right. So which means if you assume it holds at the beginning of this, at the beginning of some iteration, and if you process the body of the loop, right, if you execute the body of the loop, then it continues to hold at the end of the body. Okay. So here is the loop invariant, right. So again, right, if you assume that it holds at the beginning of the iteration, right, beginning of the body, so what happens, right, in this particular loop or in this particular body, right. So you can see that we remove something, right, from S. So since this particular loop invariant is over locations which are not in S, right, so now we need to prove this also for this location L, right, which has been removed from S, right. Which means for this location L, right, I need to show that for every successor of that location, right, for every successor L prime of that location, this mu hat k at L prime is actually greater than or equal to f at C of mu hat k of L. Okay. So this is for this specific location L that has been removed from S, right, in one iteration of this loop. Okay. But this for each loop, right, this does exactly what we want this loop invariant to show, right, because it considers every successor of this location L, right. So it considers every successor L prime of L, and then it propagates the value from L to L prime, right. So it computes this f at C of mu hat k of L, and then if this mu hat k at L prime is not greater than or equal to f, then it does a join, right. So join makes sure that the new value at the location L prime, right, which is mu hat k at L prime, this will be greater than or equal to the value f, right, which means that mu hat k at the location L prime will be greater than or equal to f at C of mu hat k of L, right, which is nothing but f, right. And this is exactly what we want to show, right. So if you assume that the claim holds at the beginning, then for each successor L prime of L, right, which is being removed from the set S, either already mu hat k at L prime is greater than or equal to f at C of mu hat k of L, which means that you don't execute this if block, right, but this will happen only if this mu hat k of L prime is already greater than or equal to this f, right, which is f hat c of mu hat k of L, or we will enter the if body, in which case we will reassign mu hat k of L prime, right, using this join with a value which ensures that this mu hat k at L prime is actually greater than or equal to f at c of mu hat k of L, right. So, for this specific location L, right, which is removed from the set S and therefore comes under our obligation, right, to show that this particular loop invariant holds, we can trivially show, right, that it holds, because that is exactly what happens in the inner for loop. Okay. So, there is one more point, right, that we need to worry about, which is that so we have shown this for the location L, right, but remember that this in one body, right, in one iteration of this loop, what all values are going to change, right. So, for every successor L prime, right, of L, the value at that location is going to change, right, the mu hat k at L prime is going to change. So, what happens if this L prime, right, this is a successor of some other L double prime. So, and suppose, right, so this L double prime, right, suppose it also does not belong to S, right, which means that it belongs to L minus S. So, if L double prime is in L minus S, right, and this L prime is a successor of L double prime, then we also need to show, right, that for this particular statement, right, C prime, which is labeling the edge from L double prime to L prime, right, this f hat of C prime, okay, sorry. So, this new value, right, which is mu hat k at this L prime, this is greater than or equal to f hat of C prime applied on mu hat k of L double prime. Okay. So, we would have to show this as well, right. Remember that L double prime is not the location that is chosen, right, this is some other location that is already outside S, right? But because it shares a successor, right, with the location L, right, and since the value at this successor L prime is changing, we also need to show that this holds, right, in the sense that whatever new value is computed at the location L prime, it still remains greater than or equal to f hat C prime of mu hat k of L double prime, right. But again, right, so you can see that this will trivially hold, because I know that the original value, right. So, remember we assume that this holds at the beginning of the iteration, right. So, at the beginning of the iteration, right, I know that the original value of mu hat k of L prime, right, this is actually greater than or equal to f hat C of mu hat f at C prime of mu hat k of L double prime, right, because L double prime is not in S, right. So, it is in L minus S, and the new value that is computed for mu hat k of L prime. So, this is the new value. So, this is the old value and this is the new value, right. So, the old value is greater than or equal to the required result, and the new value is computed by taking a join, right, of the old value. So, since the old value is greater than or equal to f at C of mu hat k of L prime, and the new value is also greater than or equal to the old value, because it is an upper bound, right. So, which means that this mu hat k new value at the location L prime, this is greater than or equal to mu hat k of old value at the location L prime, and this is because the new value is actually an upper bound, right, of the new value, and since this old value is greater than or equal to this, right, f at C of mu hat k of L double prime, and this itself is not changing, right. So, L double prime is not changing, mu hat k at L double prime is not changing, therefore, the required result follows. Okay. So, this particular case, right, where there is some L double prime such that L prime is also a successor of L double prime, which means that L and L double prime share the successor L prime. Since mu hat k of L prime is updated, we have to show that the new value is also greater than or equal to this f at C of mu hat k at the location L double prime. But since we are taking a join with the original value, and the original value is itself greater than or equal to this f at C prime of mu hat k of L double prime, therefore, the claim holds, right, for L double prime. So, this completes the proof, right, because we have shown that this is a loop invariant, and then the remaining argument follows, right, that we using that we can show that this mu hat k is a post fixed point, and since it is a post fixed point by Nash-Tarski theorem, it will be greater than or equal to the least fixed point. Okay. So, we have shown that both directions, right, LHS greater than or equal to RHS and less than or equal to RHS, right. So, which means that LHS must be equal to RHS, therefore, the Kildall's algorithm computes the least fixed point of f bar. Okay. So, this concludes the proof that mu hat k is equal to LFP of f bar, but only the final mu hat k, right. So, remember that this particular post fixed point property only holds for the final mu hat k, right. So, not for some intermediate mu hat k's.